Okay, without wasting any time, I think we should start, guys, and then the other guys will join. So last time we were doing a previous question paper, which was question 2, where we have to determine equation of motion, okay, of the undamped system for small oscillation. I think we didn't finish, and then I said I will finish it up and then send it to the WhatsApp group. So I didn't, but today or tomorrow I'll send it. I just want us to continue with this with the new topic. Okay. Today we're gonna do the respond using Runge kutta method. I don't know if you guys have gone through the notes or not. So there's this other topic. It says response using Runge kutta method. Mute.
Oh, sorry.
Response using what? Using Runge kutta. Okay, so here on respond using Runge kutta method, I hope you still remember what is Runge kutta method. We did this on mathematics 4, where we had I think we were doing second order, but here we're going to do fourth order, where we're going to have K1, K2, K3, K4. We calculated the value of K1, K2, K3, and K4. After that, we get the response from those slopes. Okay, so let's continue. Let's say we're going to imagine you have a car suspension. Okay, on that car suspension we have a spring, we have a damper, we also have a mass. Okay, that mass, it has a wheel, and then let's say if we push that object or car suspension with a constant force, the spring is gonna stretch. If we push it, the spring is gonna stretch, and then the damper is gonna resist. Okay, and then the mass moves. So I'm talking about something like this. Let's say we have something like this, where we have the spring and a damper and a mass. Okay, let's say we have something like this. Okay, so I was just saying, let's just imagine a car suspension, okay, with a spring, with a damper, and with a mass, and then the mass, it has a wheels. Okay, and if we push it with a constant force, let's say we push it with a constant force. Okay, let's say we push it with a constant force, this spring is gonna stretch, and then this damper is gonna resist. Okay, and then the mass moves, so this mass is gonna move. If let's say we're pulling it to the right, the spring is gonna stretch, and then the damper is gonna resist, and the mass is gonna move. So this is a single degree of freedom system. Okay, this is a single degree of freedom of system. So let's say from that imagination, this block, okay, we'll have a question like this: mx dot dot, okay, mx dot dot plus cx dot, okay, plus kx, all equals to force ft. Let's say, okay, here we have the force. Okay, let's say we have the force like this. So our equation is gonna look like this. This is the acceleration, velocity, and then displacement. The x dot dot is acceleration, and then x dot is velocity, and then the x is displacement. Okay, so the m is for mass. Okay, and then c, this is c, not e. C is for damping. Okay, and then we all know mass is in kg, and then damper is gonna be in what? In newtons second per meter. Okay, and then we have K. K we all know is what? Is stiffness. Okay, stiffness, which is gonna be in what? In Newton per meter. And then what else? We have the Ft. Ft is what? Is external force. Okay, we have the external force. So guys, this is just a Newton's law. F is equal to ma, but written for a spring and for a damper and masses. Okay, so this whole thing is what? Is Newton's second law. It's Newton's law. F is equal to ma, but it's written for spring, for damper, and for what? And for mass. Okay, so now let's continue. Remember, we're doing what? Response using the Runge method. So from here, we have this equation. Let me write it this side. We have the mx dot plus cx dot plus kx or equals to f of t. Okay, remember, we want to get what? A response using Runge method. A response using Runge method. So what we're going to do here, we're going to let our x, our displacement, to be equals to x, and then our velocity equals to x. I'll show you what I'm saying. So here the main reason is to what? Is to determine the response using Runge method. So this is the formula for determining what we call the Runge response using the Runge method. So it's gonna be x n plus 1 equals to, this is plus, is equals to xn plus 1 over 6 into k1 plus 2k2 plus 2k3 plus k4. So at the end, we want to determine the response. We want to determine this at the end while we are given this type of equation. Okay, we have mx dot plus cx dot plus kx is equal to f of t. So at the end, we want this equation. So we're going to determine k1, k2, k3, k4, but we won't just jump into this equation. There are some steps that we have to follow. Okay, so what we're going to do after getting the equation, we can let our displacement to be equal to something, any variable. We can also let the after letting the displacement, we can derive and get the velocity. So now from this equation, let's let x1 into t equals to x. Okay, like this. Okay, and also let's let our x2 into t equals to x dot. Okay, this is x dot into t. Okay, so guys, this is displacement. This is what? This is displacement. So here we're just assuming or letting. So we let x1 into t equals to x into t, okay? And then we let x2 into t equals to x dot into t, okay? So let's continue. This is the displacement. So we want what we call velocity. To get velocity, we're going to derivate displacement. So it's going to be what? X1 dot equals to, if we derivate this, we're going to get what? We're going to get x dot, right? We're going to get x dot t. And then if we derivate x2, we're going to get what? X dot dot. So if we derivate x2, we're going to get what? X dot dot into t. Okay, so this one is what? Is velocity. Velocity. So to get velocity, we just derive what? Displacement. So we let x1 into t equals to x, and then x2 into t equals to x dot, and then we call that what? Displacement. And then here we were deriving displacement, and then to get velocity we have to derive that. So it's gonna be x1 dot is equals to what? x dot. So here it's x dot into t, and then here it's going to be x2 dot into t is equals to x dot dot. Okay guys, so now we let x1 is equals to that, x2 is equals to that, and then x dot 1 equals to that. And then now from here we can see that we have the x dot and x dot here. Let me change the color.
Chaza. So we assume that in that diagram there's two displacements, because I see on the diagram there's just only the diagram you draw. There's x
here.
Yeah, there's only one. Yeah.
X1 here.
X1. Yeah.
Yeah. Okay. And then your question, you're asking if we what?
We are assuming that there's going to be two displacement.
No.
Because we let x1 be equal to that and x2
equals to that.
Equal to.
No. We actually I just want to substitute this x2 here. So we just let x2 to be equals to this one, and then x1 equals to what? To this one. Okay. We only have one displacement, and then here we just let x1 to be equals to what? To this x. Okay, and then we let x2 to be equals to what? To this one for velocity. After that, we're going to derivate and then get the velocity. Okay. Yeah. Here is just assumption. Yeah, we're assuming. Yes. Okay.
Right.
Yeah. And then after our derivative, you can see here we have the x dot and on the displacement, and then we also have the x dot on the velocity. So we can say therefore our x1 dot into t is equals to x2, because they are all equals to what? To x dot dot. To x dot. Do you get it? This x dot and then this x dot, they're equal. So therefore we can say that what? X dot to x1 dot into t is equals to what? To x2 dot. To x2 into t. Okay. And then after that, we can just substitute this back to our equation. Oh guys, before we continue, we call this thing, the one that I say we're gonna assume, we call them state space. Okay, we call them state space. When they say determine the state space, you know that you're just gonna assume or let any variable. You can use any variable here. You can use y, you can use z, p, any variable. So now I use x1 into t is equals to x. This x. Okay, so here you can use any variable when it comes to state space. So this part we call it state space. Okay, when we're assuming. Okay, sharp. Now we said we have the x dot and then the x dot. Therefore, we're gonna say the x1 dot into t equals to what? It's equals to x2 into t. Okay, and then moving forward, we're going to substitute this state space into our equation. Remember, we have the x dot dot, the x dot dot it's what? It's x2, and then we have the x dot is what? Is x2. It's this one. Okay, and then we have the x into t, we have what? x1t. So we're just going to substitute the state space into what? Into our equation. So now let's continue and then substitute the state space into our equation. So we have the x dot, so our x dot is what? Is x2 into t. We have the x dot dot, our x dot dot is what? Always is here, it's x2 dot. Okay, and then only x is what? Is x1. So now let's move forward. Remember, we have the mx dot dot, okay, plus cx dot plus kx is equals to f of t equals to f of t. Okay, so now from our state space, our x dot dot is this one. It's equals to what? It's equals to x dot 2. So now this side we're going to write mx. We're going to rearrange the equation and now substitute the state space. Okay, so we're going to have m x dot 2 mx2 into t plus c. X dot, our x dot is what? It's x2, and then our x, it was x1 t, or equals to f of t. Okay, or equals to f of t. And then from here we can we can write our equation in a matrix form. We can write our equation in a matrix form. Okay, we can write it in a matrix form. So we can just write with x1 and x2, and then or before that we can make x dot 2 subject to the formula. So we're going to have x2 dot, okay, if we're making it subject to the formula, and then we're going to divide both sides by what? By m. So it's going to be equals to f of t divided by m minus c over m x2 t, okay, plus, I mean it's minus, not plus, because we're taking this to the other side. We're making x dot subject to the formula. Okay, and it's going to be minus k over m x1 t, like this. Okay, and then after that we're gonna write our equation in a matrix form. Remember, on the other side we said x dot 1, where is it? Let me just go back. So this side we said x1, oh chesa, and then this side we said x1 dot into t equals to what? Is equals to x2 into t. Okay, we have x1 dot equals to x2 t. Okay, like this. So now we have these two equations. We have the x1 dot and then the x2 dot. Okay, from the assumption, okay, from the state space. So now let's write our equation in a matrix form. So to write our equation in a matrix form, we're going to write it like this. We're going to have x dot 1 and then x2 dot, okay, equals to into, so we're going to have x1 and then x2 like this. Okay, plus this side is going to be for the force. It's going to be for the force. Okay, so this equation, the matrix form is from this formula where we have the x dot equals to ax plus bu. So this one is for force, and then this one is for b is for what do you call, coefficient of the force, and then u is the force, and then a is for stiffness and damper. Okay, and then this one are the coefficient, the x and y, the displacement. Okay, so now let's continue from our two equation. On x1 we don't have x1, so it's going to be 0, and then we have x2. The coefficient of x2 is going to be what? It's going to be 1, and then we don't have the force here, so it's going to be 0. And then on the second equation, x2, we have x1, which is what? Which is negative k over m. Negative k.
Which two equations did you say we are using? Sorry about that.
No problem. Let me highlight them. We are using this one and this one. Okay, we're using that one. So we have the x dot 1. On x dot 1 we only have x2 into t, so it's gonna be, on x1 we don't have anything, that's why I wrote 0, and then in x2 we have x2 here, so we're just gonna write the coefficient of x2, which is 1. And then now we're gonna go to x2 dot, okay, and then we check x1. Our x1 is what? Is negative km. Negative k over m is this one, and then we're gonna check x2. X2 is gonna be what? A negative c over m. like this. And then the force, we have positive Ft over m, and then we have force here, so it's going to be 1 over m, which is going to be what? 1 multiplied by F, which is going to give us what? Ft over m. Okay, it's gonna look like this. Our matrix is gonna look like this, or we can write it like this. The matrix form from the notes, if you went through the notes, they make F subject the formula where they wrote the matrix in this form. So they have F1 and then F2, okay, where they say x1 x2, okay, like this. And then here they have 0, and then on the textbook, actually they didn't write the displacement on top, they just wrote it here inside the matrix. So this is how they wrote it, where they have x2 and then 0, and then here they have negative k over m, and then here they have negative x1, and then here they have negative c over m x2, and then here they have force f of t over m. So on the notes, they wrote our matrix like this. It's still the same thing as what we wrote on the other side. It's still the same thing. So we have the negative k over mx1, negative c over mx2. So guys, it's still the same as this one. Where is it? Is this one. We have the negative k, which goes with x1. We have the negative c over m, which goes with x2. We have the force here. So we're gonna use this one. Still the same thing, but we're gonna use this one from the notes, okay? So after writing our what we call our matrix, that's where we're going to apply what? The Runge formula, okay? The one that I wrote here. Where is it? Did I write it? I didn't write it. Okay, I'm gonna show you now. Okay, so Runge is like taking four gases. I mean gas actually, let me say taking 4 gas of the slope. In each step we're gonna have the beginning, we're gonna have the middle, and we're also gonna have the end, and then averaging them smartly to get what? To get the next point. So the formula for Runge is xn. I think I wrote it, man. I did. Where is it? I think I did, you know. Yeah, it's this one. Yeah, it's this one. So now we're going to use what? The Runge formula. So it's xn plus 1 over 6 k1 plus k2 plus 2k2 plus 2k3 plus k4. Remember, the main objective here is to what? Is to get the response using what? Using the Runge method. Using the Runge method. Now we can use it after getting the matrix. Okay, after getting our matrix table, we're gonna use this matrix to use. We're gonna use it to get what? To get the Runge, the response using the Runge. Okay, so from here we have that formula xn plus 1, which is equals to xn plus 1 over 6 k1 plus 2 k2 plus 2 k3 plus k4, okay, like this. And then now from here we're going to determine the value of k1, the value of k2, and the value of k3 and k4. So to determine the value of k1, we use this formula is hf. H is for step size, and then F is the forces. So the forces, we're gonna use this matrix. We're gonna use this matrix to determine what? To determine the forces, okay? So the main reason to determine when we start by doing the state space and then the matrix is to get the values of F, okay? So K1 is equals to HF into T and then or X. So T is the time and then X is the displacement, okay? And then K2, to determine K2 is going to be HF. Remember, H is the step size, and then into T plus h over 2, okay, and then comma, x plus k1 over 2, okay, and then this is the formula for k2, and then k3 is equals to hf, okay, into t plus h over 2, comma, then we're gonna have x plus k2 over 2, okay. So this is the formula for k3, and then k4. To calculate k4, guys, for sure you still remember this from maths 4, okay. And then k4, we have h multiplied by f into t plus h, comma, x plus k3, okay, k3. So this is how this is the formula of calculating the value of k1, k2, k3, k4, okay. And then you'll be also given the initial condition. They'll give you, okay, x1 is equals to 0, and then x2 is equals to 0 or 1. They will give you the initial condition. So guys, this thing, the k1, k2, the slope, we call them slope, is just a recipe. So you're going to compute 4 slopes, k1, k2, k3, okay, and then combine them. After combining them, step forward, and then you're gonna get what? You're gonna substitute here into the equation and then get what? The response, okay, and get the response. That's what we're going to do. So the first thing, you'll be given equation mx dot plus cx dot plus kx is equals to the force, okay. You'll be given something like that, and then you'll also be given the initial condition. You'll also be given a time which is divided into maybe equal steps. That's where you're going to get what? The step size. After that, you just follow all the steps. So the step 1, you have to write the equation in a first order form. So to write the equation in a first order form, you have to do what? The state space, where you assume or let the variable to be equals to something. So now I want us to do example. This example, actually it's not, it is example from here. Don't know if you can see. Where is it? No, not this part. Yeah, it's here. So here I was just showing you this Runge kutta thing, and then this is the formula that I was talking about, okay. The f1 into t, f2 into t, and then we have the x2 minus what. So this is the formula that we're going to use. This one, on top of the Runge kutta method, we're going to use this formula, and then after using that formula, we're going to use this formula to get what? To get the response. So it's half, it's 1 over 6 k1, so, and then this the formulas for calculating k1, k2, k3, k4, okay. And then here they say respond using the Runge kutta method, where we have what? They say find the response of the single degree of freedom system subjected to a force with the equation of motion. So here we are given the equation of motion, which is 500 x dot plus 200 x dot plus 750 x is equals to 50 is equals to 2000, okay. And then the 500 is mass, and then 200 is damper, and then 750 is what? It's spring K, and then we have the force, which is 2000. And then they say what? Use the Runge kutta order, use the fourth order Runge kutta method, and then assume the initial condition as this. We have x into t is equals to 0, x0 is equals to 0, and then velocity is equals to 0 2. Okay, so now I'm going to show you all the steps that we have to follow when we are using what? The fourth order Runge kutta method, okay. So now let's go back to the whiteboard and then do that problem, okay. So on that problem, we are given the equation of motion, okay. We are given the equation of motion where it was 500 x dot. No, I'm not using the right pen. we are given 500 x dot dot, okay, plus 200 x dot plus 750 x equals to f of t, which is what? Which is 2000. And then we're also given the initial condition. They say x of 0 is equals to 0, and then x dot of 0 is equals to 0. Okay, and then there by the bottom of problem, we're also given time. So they say t is equals to 20 seconds. Okay, and then which is what is divided into what? It's divided into 400 equal steps. Okay, so this information is going to help us to determine what? To get the step size h. Remember, on our equation of Runge kutta, we have hf. So to determine the h, it's gonna be what? It's gonna be 20 divided by 400 and get what? And get the value of h. So our h, or change in t, is gonna be 20 divided by 400, which is going to be what? 20 divided by 400, which is going to be 0.05. So now we have the step size, we have the equation of motion, we have the initial condition. This is the initial condition. So remember, the first step is to write our equation in a first order form. So we're going to write this equation in a first order form. So the first step, number 1, write the equation in first order form. So when we're writing our equation in first order form, we're going to use what? Write the state space. We call them what? State space. So when we're talking about the state space, we're going to assume or let. Okay, so we have that equation, which was 500 x dot dot, okay, plus 200 x dot plus 750 x is equals to 2000. Okay, we have this equation. So we want to write our equation in a first order form. So to do that, we have to write what? The state space. So to write the state space, we have to let. So we're gonna let x1 into t equals to what? Equals to x. Okay, because here we're dealing with the x value. So here it's x dot. Okay, and then here we have another dot. Okay, and then we're also gonna let x2 to be equals to x dot. Okay, like this, x2 equals to x dot. Okay, and then now after that, we're going to derivate our displacement. So to derivate, we're going to say x1 dot, we're going to derivate x1 dot, okay, into t. So derivative of x1 dot is going to be what? It's going to be x dot. Okay, x dot. And then derivative of x2 dot is going to be what? It's going to be x dot dot. Okay, like this. And then now we can see we have two dots here. We have this one and this one. They're the same, which means we can say therefore x1 dot, it's equals to what? It's equals to x2. Okay, guys, do you have any questions so far? So this is our first step. Guys. We have to determine what to write equation in a first order. Okay, after getting this velocity and displacement. So we're going to write this, we're going to substitute the state space into what? Into our equation of motion. So wherever there's x dot dot dot, we're going to substitute with the x2 dot, and then wherever there's x dot, we're going to substitute with what? With x2, and then wherever there's x, we're going to substitute with what? With x1, so that we can get what? We can write our equation in a what? In a matrix form. Our equation in a matrix form, okay? And then after writing our equation in a matrix form, we're going to use the Runge kutta method. Okay, now let's move forward. So we're going to substitute this. Step 2 is substituting the state space. Okay, step 2, number 2, substitute state space. Okay, so we're going to have, wherever there's x dot dot, we're going to substitute with x2. Okay, so it's going to be 500 x2 dot plus 200 x2, okay, plus 750 x1, or equals to what? To 2000, which is what? Which is f of t. Okay, but there's no need to write this. F of t, okay, like this. Here we just substituting this, what we call the state space, and then we can write our equation in this form. Sorry, in this form. We can write it in this form. So I showed you how to write it, how to write the matrix in this form on our previous example where we were not using the values. Okay, so what we're going to do, we can just make x2 dot separate the formula, or we can just copy the matrix form from from our notes. But let me not just copy, let me just show you how to write this matrix form. Remember, we had the x1 dot into t, which was equals to x2. Okay, like this. And then now we're just gonna make this x2 separate the formula. So it's gonna be x2 into t equals to, and then we're gonna take everything that is on our left hand side to the other side. So it's gonna be 2000, okay, divided by 500 minus 200 over 500 x2, okay, and then minus 750 over 500 x1, like this. And then from here we can write in a matrix form. We can write it like this. This is dot, or equals to, and then we're gonna have the x1 and then the x2 plus, here we're gonna write our forces. Okay, and then now we're gonna check on our x dot 1. Do we have the value of x1? No, so we're gonna write 0. Do we have the value of x2? Yes, we're gonna write the coefficient of x2, which is 1. And then we go to x dot 2. Do we have the value of x1? Yes, which is what? Which is minus 750 over 500. And then do we have the value of x2? Yes, which is what? Which is minus 200 over 500. Okay, do we have the value of force on x1? No, so it's going to be 0. And then do we have the value of force at this on our second equation? Yes, so the force here it's 2000. So now here we can just write 1 over 500. And then we know that here, or on the force, is what? It's 2000. So it's going to be F multiplied by 1, which is going to be 2000 divided by 500. Still the same thing. Okay. Or we can write our equation like the one that is on the notes, like this, where we have F1, F2, where we have x2 here, and then we have minus 750 over 500 for x1. Okay, minus 200 over 500 x2. So here on the first equation we don't have x1, and then we have x2, and then here we don't have the force, and then here we have the force, which is positive 2000 over what? Over 500, like this. We can write our equation like this. Okay, still the same thing. And then from writing our matrix, we can use the Runge kutta. Remember the formula for Runge kutta? It's xn plus 1 is equals to xn plus 1 over 6 k1 plus 2 k2 plus 2 k plus 2 k3 plus k4, and then we'll be looking for k1 and k2 k3 k4. So from here we're going to look for that xn. We're going to look for that, and then other formulas. I think here it's going to be k22 and then plus 2k3 plus k4. Okay, and then we're going to have this. So here we're going to have k1. We're going to start by calculating k1. Okay, k1 is equal to what? hf into tx. Okay, and remember the t is time, so we're gonna start at t is equals to 0 and then at x equals to 0. Okay, that's where we're going to start. So this x, it's the initial condition. So we were given that the initial condition is 0. So for x1 and x2, so which means, let's say this one is going to be 0 and 0 for x1 and x2, since we're going to deal with what? With this matrix form, which is going to be what? X1 and x2. So our initial condition is like this. It's going to be x is equal to 0 and 0, 0 for x1 and 0 for x2. Okay, now let's continue and calculate the value of k1. So now let's continue and calculate what? The value of k1. So now what we're going to do, we're going to start with the f, because remember we already have the k. K is the time that we're given and the step divided. So it was 20 divided by 400, where we got 0.05. Yes, got 0.05. So now our k1 is going to be h multiplied by f. So f, remember on f we have this one, and then we also have this one. We have two f's. Okay, so to make things simpler, we're just gonna substitute our values. So here we have x2, we have x1, we have x2. So remember we said our x here, the initial condition was what? It was 0 and 0. So what we're going to do, we'll start by calculating this part first, and then after calculating it, we're gonna multiply with h to get what? To get k1. So now let's calculate f into t multiplied by x. So it's going to be f into t0. We're going to start at 0 and then x0. Okay, it's going to be equals to, and then remember our t is going to be 0 and then our x0 is going to be 0. So here we're just going to write our matrix. So it's going to be x2 minus 750 minus 750 over 500 x1. Okay, and then here we're going to have minus 200 over 500 x2, and then here we have 2000, okay, over 500. You guys, but I think you can hear me here. It's just 2000. This is just 2 kilometer, 2k over 500. There's no space. Let's say 2k over 500. It's on the side, guys. It's not close to. There's space between x2, x1, and this 2000. Okay, so we have this, and then now we're saying we're going to start t at 0 and then our x at 0, 0. So which means this x is always gonna be what? 0, 0. From what? From the initial condition. IC stands for initial condition. Okay, t is gonna be 0 and then x into 0 is also gonna be 0, 0. From what? From the initial condition. So what we're going to do, remember we have the f into 0, and then here we're gonna write our what do we call our displacement like this from the initial condition. Okay, and then here we have x2, and then we have that 750 over 500, and then we have minus 200 over 500. Here we have x1, here x2, and then we have 2000 over 500 here. Okay, so here we're going to have the value of t, and then this one's going to be x1, and then this one's going to be x2 from the matrix. So wherever there's x1, we're going to substitute with 0, and then wherever there's x2, we're going to substitute with 0. So we're going to have our f as 0, and then minus 750 over 500 times 1, times 0 is going to give us 0, and then minus 200 over 500 times x2, which is 0, it's going to give us 0, and then 2000 divided by 500 is going to give us 4. So which means our f here, we're going to write it in a vector form. It's going to be 4, because it's going to be 0 on top, and then 0 plus 0 is 0, and then 0 plus 4 is 4. So which means our f is going to be 0 to 4. Remember, k1 is equals to what? HF, like this, HF, which means it's going to be what? Our h it was 20 over 400 from the initial quotient into 0 and 4. We're going to write it in the matrix form. So 20 divided by 400, which was 0.05, 0 and 4. So our k1 is going to be 0.05 multiplied by 0, which is 0, and then 0.05 multiplied by 4, which is what? Which is going to be multiplied by 4, which is going to be 0.2. So our k1 is equals to 0 and 0.2. So we have the x1 and x2. So at the end, we're going to have the displacement, respond for displacement, and respond for what? For what do you call? For velocity. So now this is how we calculate k1. K2, we're still going to do the same thing. So the formula for k2 is equals to hf into t plus h over 2, and then we have x plus k1 over 2. Remember, we already have the value of k1, which is 0 and 0.2 in a vector form. Okay, so now let's continue and calculate calculate k2. So to calculate k2, we're just gonna start with x plus k1 over 2 equals to, remember, x is 0, so we have 0 and 0 on x plus k1. So let's just take this half outside, and then inside we're gonna have k1. Remember, our k1, it was 0 and what? And 0.2 and 0.2. Guys, do you have any question? Guys, do you have any question? Hello?
Yeah, I was finding the K1, K2, it's a bit challenging.
Is it?
It's a bit confusing for me. I don't know about the others.
Okay, let me explain again on K1. Remember, the formula for K1 is from the Runge kutta. Okay, formula for K1 is this. K1 is equals to HF into T, comma X, okay? Like this. And then we are given the initial condition, and we're also given the time. On our initial condition, they say x into t is equals to 0, and then this one is equals to 0, and then we have x dot into t is equals to 0, which is equals to 0. So which means this t is gonna be 0, okay? Even this x, on this x, remember we have the x1 and x2, so we're gonna write our x in a vector form. So our x here, let's say this one's gonna be t0, and then this one's gonna be x0. So which means our t0 is gonna be 0, and then our x0 is gonna be 0 from what? From the initial condition, okay? From the initial condition. So what we're going to do here, we're gonna start by focusing here. ftx0. So we have the formula of f, which was in a matrix form, where we have the x2 minus 750 over 500 x1, and then we have minus 200 over 500 x2, and then we have the force divided by mass. Okay, so now here on x0 we have the x1 here, and then here we have the x2, and then our t is 0. So to determine the f, we're going to use this matrix. Okay, so to determine that matrix, we're substituting the value of x1 and x2. Our x2 is what? It's 0. So here we're gonna have 0, and then our x1 is what? It's 0. So it's gonna be minus 750 over 500 times 0. So it's gonna be 0. Okay, and then minus 200 over 500 times 0, which is what? It's gonna be 0. And then here, remember, we have the force divided by mass, so it's gonna be 2000 divided by 500, which was 4. Okay, so we're gonna get the value of k1 and k2 in a vector form. Okay, where we're going to have x1 and x2. Remember, when we were assuming on the state space we have x1 and x2. Okay, so at the end we're going to have the velocity and displacement. So to see that we're going to have to have the displacement and the velocity, we take it from the initial condition. Remember, our initial condition, we were given the displacement and the velocity. So which means at the end of this equation, when we determine the response using the Runge kutta, we're going to have the x1, which is displacement, and then x2, which is velocity. Okay, that's why here we're going to have what? We're going to write it in a vector form, where we're going to have two values. So from here, after getting the value of f, it's f is equals to, f into, okay, no, it's f is equals to, yes, f is equals to into, we have 0, and then here we have three values, so it's gonna be 0 plus 4, which is 4. And remember, the value of k1 is what? It's h multiplied by f, and then now we get our f as 0 and 4, so it's gonna be h which is what? Which is 0.05 multiplied by what? By 0 and 4. So to get k1, it's going to be 0.05 multiplied by 0, and then you get 0, and then 0.05 multiplied by 4, you get the 0.2. From here, where is it? It's this one. Yeah, I was explaining the k1, and I don't know if you get it. But if you practice, you'll get it. And then when you start, you're just gonna ask me how did we get that. Okay, so now let's continue and do k2. This is the formula for k2, and then I said we're gonna start with this part, x plus k1 over 2. Remember, our x is 0 and 0 from the initial condition, and then here I just took this half, and then inside I put the value of k1. Remember, we get k1 as 0 and 0.2. okay, after that we're gonna multiply this 1 over 2 with 0, and then 1 over 2 with 0.2, and then get what? The value of k1 over k2. Okay, after that, let me erase this one and then continue getting k2. Sorry. Okay, and then now we're still based on k2. We start by getting x plus k1 over k2. Remember, the x from the initial condition are 0, 0, and then we calculate this, so it's going to be half multiplied by 0, and then which is going to be 0, then half multiplied by 0, 2, which is going to be what? Which is going to be 0.1. So we have 0.0 and 0.1. So after here, let's calculate the fourth f. Remember, f is x2 minus 750 x1. Let me just make this, and then here we have 200 over 500 x2. okay, and then here we have 2000 divided by 500. okay, like this. We have this. Okay, so now this one is x1 and then this one is x2. So now to determine the f, wherever there's x1 we're going to substitute with 0, wherever there's x2 we're going to substitute with 0.1. So our f is going to be what? It's going to be 0.1, and then this one, negative 750 divided by 500 times 0, it's 0. Okay, and then here negative 200 over 500 multiplied by 0.1, it's gonna be what? It's gonna give us a negative 0.04. Okay, and then here 2000 divided by 500, it's what? It's 4. Okay, and then therefore our force is going to be 0.1, and then here we're just gonna add. So 0 minus 0.04 plus 4 give us what? Give us 3.96. So this is our force. And remember, K2 is what? It's HF into T plus H over 2, and then X plus K1 over K2. Okay, what's left? Okay, yeah, we're just gonna calculate K2. So K2 is gonna be H multiplied by F. Our F is going to be this 0.1 and 3.96. So it's going to be 0.05 multiplied by 0.1, and then 0.05 multiplied by 3.96, and then get the value of K2. Okay, guys, and K3 you do the same thing up until K4. After getting the value of K4, you substitute back to what? To our equation, the x, what do you call this one? Xn plus 1. Where is it? After getting the value of K1, K2, K3, K4, you substitute back here. So it's going to be x0 plus 1 is equals to x0. And remember, our x0, it's 0 and 0. So when you substitute here, K1 is going to be 0 and 0.2. K2 is going to be 2 multiplied by 0 and what to call 0.1 and 3.96. So and then you're gonna get the values. So this is what I'm saying. Remember, we have this. So it's gonna be this plus these values. Okay, so it's gonna be x1, okay, is equals to, and then x0, remember from the initial condition we have 0 and 0 for x1 and x2, plus 1 over 6, and then we get our K1 as what? K1, it was how much? It was 0 and 0.2. okay, let me not write the bracket here. Okay, plus 2 into, let's say K2 we got as 0 and 0.1. I'm just making an example. Okay, and then K3, let's say K3 we get 0.005 and 9. Okay, I'm just making an example here. Plus, let's say K4 we get as 1 and 2. Okay, and then what you're going to do here, we're going to have the x1, the top part. This one is x1. Everything that is on top is x1. Okay, x1. So to get x1, we're going to say 0 plus 1 over 6 into 0. Okay, plus this one, 2 times 0. So it's going to be 2 into 0. And then plus 2 into 0.05 plus 1. Okay, and then on x2 is still going to be the same, but using what? The bottom part. Using the bottom part. So this is how we determine response using the Runge method. So the first step is to write our equation in a first order using the state space, and then after that you write in the matrix form. After writing the matrix form, that's where you write the Runge formula. Okay, and then you calculate the K1, K2, K3, K4, and then you substitute back to what? To the equation, and then you get what? X1 and X2. Remember, the X1 is what? Is displacement, and then X2 is what? Is velocity. So this is how we do it, guys. Do you have any question or you don't understand it, guys? Hello?
Hello. I don't have any question. I think I took a recorder, so I'll just have to look back, then I think we'll be fine.
Okay.
Because it's just everything for me now.
Okay, no problem.
Yeah.
So this is how we do it. I think I'll just write it on the paper. I'm promising. I'm going to write this problem or example in a paper step by step with showing you how to calculate this, because here my handwriting is bad. So I'm just gonna write it in a paper and then scan it and send it to our WhatsApp group, and then you'll see step by step, or okay, this is how we calculate it. Maybe there it will make sense. Okay, and then guys, on Thursday it's solid mechanics class. Okay, next week Tuesday when we meet, we're gonna do the eigenvalue and the natural frequency. So just to show you what we're going to do next Tuesday, in this topic, the topic that we're going to do, the eigenvalue and the natural frequency, the main objective there is to determine the normalized stiffness. So under eigenvalue and natural frequency, so here under this, the main objective here is to determine what we call the normalized stiffness. We're going to determine the normalized stiffness, where we have the what do we call the formula for normalized stiffness, which is formula for normalized stiffness is what? It's K, it's half K and another half. So this is what we're going to do. Still, this mass is going to be from the matrix, and the K is also going to be from the matrix. So the main objective here is to get the normalized stiffness. We call this K with the prime on top, we call it normalized stiffness. Okay, normalized stiffness. And then also we're also gonna this is the first one, and then the second one we're gonna get the natural frequency, and then the third one where we're gonna get the eigenvalue and vector. Okay, value or vector. Okay, and then the last part where we're going to determine the modal matrix and the spectral matrix. So this is what we're going to do. So this is the main objective of our next topic. We're going to be determining the normalized stiffness. We're going to also be determining the natural frequency, eigenvalue or vector, and then we're going to determine the modal matrix. A modal matrix. Okay, so this is what we're going to do. I think we're going to stop here, and then I'll send this problem, the one that we will do with the Runge kutta one, and then you'll see step by step. Okay guys, thank you. We're gonna stop here, and then we'll continue next week Tuesday.
Okay, yeah, please send the video also when you get time.
Yes, I'll upload it and then send it to you.
All right, thanks.
Sure.